Hi guys, welcome back. In this video, we are going to discuss about Zenor diode. Zenor diode. First, I will give a brief introduction about what is meant by Zenor diode and what is the use case of this Zenor diode and what is the need for using this Zenor diode. Just let's go through it. When used in regulatory circuits, the Zenor diode must have a current entering it limited. If a perfect voltage source was placed across it, it would draw excessive current once the breakdown voltage has been reached. Right? In a normal PN diode, if you are going to apply what we call reverse, if you are going to connect it in a reverse bias, and if you are going to apply what we call breakdown voltage, I mean, you know it, what is meant by breakdown voltage, the whole what we call diode is going to be damaged, and which in turn will damage the whole circuit. To overcome this issue, we came up with a new idea of Zenor diode. What is it going to do? Let's look at it. To overcome this, the Zenor diode must be driven by a current source. Here in PN junction diode, we are driven by voltage source, right? We are connecting, and the whole diode is functioning on the basis of voltage difference. But here we are going to, in Zenor diode, we are going to regulate the whole diode by using current source. This will limit the current to chosen value. Yeah, if we are going to drive it through an current source, we can regulate the current and we can choose the value what we need. The value of the series resistor is simply to calculate. It is simplify the voltage across the resistor divided by the current required. The level of Zener current can be chosen to choose the circuit and Zener diode use. Yeah, just look at this representation. We are going to connect it to an between what we call positive and electrode. Right here, we are not connecting to a zero. I mean negative voltage. We are connecting it to a zero voltage, which is going to be base for our condition, and we are connecting a resistor in front of the diode, which can regulate the flow of current through the circuit. And if the voltage is excessive, we are going to take out that voltage through here, so that we are going to save our diode, and which in turn we are going to save our whole circuit, right? That's the purpose of Zenor diode, and this is a typical representation of a Zenor diode connection. Just remember the circuit. Applications of a Zenor diode, where this application can be used in voltage stabilizers, right? We are the current, the voltage from a line what we have in our houses will be very fluctuating. If you are going to use that voltage fluctuation directly with of any of our electrical appliances, it's going to be damaged confirmed. The damage of appliances is confirmed. So we have to stabilize the voltage. The device which is used to stabilize the voltage is known as voltage stabilizer. In that stabilizer, we use this Zener diodes, reference voltage limiter circuits. I don't know about this. These are the applications of a Zener diode. And now we are going to look at the biasing of this Zener diode. Just look at it. The VA characteristics of a Zener to voltage reference diode is the key to the operation. In the forward direction, the diode performs like any other diode, normal diode, but in reverse direction, whereas its specific performance parameters can be utilized. Just see, in forward biasing, it's going to be perform like a normal PN junction diode. In reverse biasing, just look at it. As we have positive and resistance, pardon the drug, and we have another source to take out this voltage, we can regulate this voltage, right? If you are going to apply what we call, and it's a Zener diode, it's an electrical representation of Zener diode, and its base or 0 volts, or we can connect it to even negative terminal also. It's not a problem. I'm just, for my use case, I'm representing it as a 0 voltage base. Just look at this specified voltage. What is meant by specified voltage? Even if I'm going to apply high voltage over here, I can take it out here, right? And I can maintain my Zener diode, what we call, safe. This can be, so this applied voltage can be varied if I'm going to take out the voltage out here. Yeah, so it can be any voltage as we require, right? This can be any voltage. Whatever the voltage, we can take excessive voltage from here. That's what here specified voltage means. Okay, I think you guys got an what is the application of Zenor diode. I hope so. Although the voltage difference diode is normally referred as a Zenor diode, there are two different breakdown mechanisms can be occurred. Just this is a reverse breakdown. If we are going to apply reverse what we call reverse breakdown voltage without this output, here we can observe two types of breakdown. One is Zener effect and another one is impact ionization effect. The limits of voltage are given over here. If the voltage is less than 5.5 volts in reverse biasing, if the voltage is less than 5.5 volts, the Zener effect will predominate. And if the voltage is greater than 5.5 volts, the impact ionization is going to affect. This is what we discussed: impact ionization, continuous circulation of electrons and impact with the depletion layer, and predominantly it's going to break down. Now we are going to discuss about what is Zener effect and what is the difference between both of them. Yeah, just look at what is meant by Zener breakdown. In Zener breakdown, the electrostatic attraction between the negative electrode and the large positive voltage is so greater. Then it pulls electrons out of their covalent bonds and away from these parent atoms. That is, electrons are transformed from the valency to the conduction band. In this situation, the current will be still can be limited by the limited number of free electrons produced by an applied voltage. So it is possible to cause a Zener breakdown without damaging the semiconductor. The importance are, just look at this. If you are going to use what we call um I mean it's an typical PN junction diode. Just consider these electrons. These are positive electrons, and this is connected in an reverse bias, right? Negative is connected with positive, and positive is connected with negative. So just consider this is the flow of electrons, and it will reach here. As electrons are flowing in this direction, the current will start flowing in this direction, and because of these what we call increasing depletion layer, up to certain amount the current will be restricted for flow. As the all the electrons are coming out, and all the what we call positive ions are going in. Here we discussed, right? Here we are going to have a certain layer of adjacent layer, right? This layer will attract these positive ions, and the layer adjacent to it will attract negative ions. These adjacent what we call adjacent layer electrons or protons will not go come out. That's what the whole purpose of the depression layer. Increasing in reverse biasing, the depression layer will increase, right? That's what I mentioned, right? And this will lead to Zener effect. This is the Zener effect, a small current flow. I hope so. Both sides of what are the impacts, important points of an Zener breakdown. Just go, just look at it. Both sides of p-n junctions are heavily doped. That means large density of electrons are present, large density of positive ions are present. Depletion layer is narrower. In a p-n junction diode, after doping, the depletion layer will become, it's going to become narrower. In this type of p-n junction diodes only, Zener breakdown is going to be possible. A strong electrostatic field is produced. Large number of holes and electrons are produced. Zener current is independent of applied voltage. Yeah, it's going to be independent of applied voltage, right? Whatever might be the voltage, the current will flow. Because as it is in positive terminal, the negative electrons will attract towards it. Whatever might be the voltage, even if it's going to be very less voltage, also the electrons will be attracted towards it, and current will start flowing. Avalanche breakdown is what we discussed. Impact breakdown. This is the whole theory regarding it. We will discuss what are the key points to be remembered. Both sides of p-n junction are highly doped, because to form an diode we have to dope it very highly. Depletion layer is large. Yeah, that's what we discussed. It's going to increase. Electrostatic field is not so strong. Electron hole pairs are generated. Charge carriers acquire energy from the applied potential. Yeah, in avalanche breakdown, this applied potential is going to play a key role, because if you are going to increase this voltage, the velocity of electrons will increase. If you are going to decrease this applied voltage, the velocity of electrons will decrease, which will result in what we call, which will have an impact on the depletion breakdown of this depletion layer. If it's going to impact with high velocity, the depletion layer will break down very soon. If it's going to impact with less velocity, the breakdown will take large time. That's what I have mentioned. The charge carrier acquire energy from depletion applied potential itself. Yeah. I hope you guys got an basic idea about Zenor diode and its applications. This is up to this video, guys. Thank you. Meet you in the next video, guys.